Hi everyone. Today we are going to move on from talking about just the sun and begin talking about other stars and stars in general. So for this lecture, we're going to think about units. So the unit of AU, of light year, and a new unit called the parsec. We're going to look at visual magnitude, absolute visual magnitude. We're going to go over and explain the Balmer thermometer and how we can use it to determine the temperature of a star. Then we're going to get into reading and understanding HR diagrams. So when we think about stars, we have to think about their source of energy. So there's two types of nuclear energy. On Earth, we have what is called nuclear fission. So this is the nuclear power that we use on Earth. It is what is happening in nuclear reactors, where large nuclei are being broken into smaller pieces. So it's generally uranium that is used. So this is here we have a larger atom. Nuclear fission is where we split that into two smaller atoms. In a star, we have what is called nuclear fusion. So this is what the energy that's generated within a star, in the core of a star. This is where hydrogen is actually fusing together to form helium. So here we have two hydrogen fusing together, fusion, to form a larger atom. So we've not been able to create nuclear fusion on Earth. On Earth, all of our nuclear energy is in the form of nuclear fission. So there is a difference. We do not have the same type of energy creation that's happening within a star here on Earth yet. It is definitely an active area of research. So we have energy being generated in the core of a star by nuclear fusion. So this is creating photons that are very, very, very high energy, incredibly high energy. They are in the gamma ray wavelength, very hot, around 16 million Kelvin. These photons will bounce around as they drift outward. So they don't travel directly outward from the core to the surface of the star. They drift around in rather random patterns while the overall motion is outwards. So as the photon is moving away from the core, it's actually converting to lower forms of energy as it moves away from the core through what we call the radiative zone. So we have the core of the star, and then we have the radiative zone. So this is where we have photons bouncing around, transitioning to lower forms of energy as they move outwards. Once they reach the surface of the radiative zone, we have what is called the convective zone. So the convective zone is where the gases towards more of the surface of the star are being convected. So because of the heat in the core in the radiative zone, we have convection occurring, where the gases closest to the radiative zone are very, very hot, so they warm up, and then they rise to the surface of the star, where they will cool down because now they're further away from the radiative zone in the core. The colder gases will then sink down, rise up. It's similar to boiling water. So that convection is happening in what we call the convective zone. So here's a diagram with lots of labels. So we have the core of the star. This is specifically our sun, but remember that our sun is a very average star. It's similar to almost every other star. The core of the sun, the core of the star, then we would have this yellow is the radiative zone. The red area here is the convective zone. And then we have our photosphere, which is the surface. Above the photosphere, we have the chromosphere. Above the chromosphere, we have the corona. So those are the layers of this star, well, our sun specifically, from the core outwards towards the end of its atmosphere. So something important when we think about stars and thinking about looking at stars, comparing stars to each other, is how far away is the star from us? What is the distance to the star? There is no ruler large enough to measure the distance to a star. So what we use is what is called parallax. So we've talked about this before. It's the apparent motion of an object due to the fact that the observer is moving. So for example, I'm sitting in front of my window right now, and if I look outside with just my left eye, I see the trees within the window frame with the window panes in the middle. If I switch and I look at the right eye, and I look out only my right eye, the trees appear to have shifted within the frame of my window. But that's because the point of view, being my two eyes, are set apart. So because I have two eyes, when I look at one versus the other, it looks like what I'm looking at has shifted. But I know that the trees outside of my house did not just move. It's only because my position changed from my left eye to my right eye. So this also happens with stars, just on a much larger time scale. So if you're over here at this viewpoint A, looking at this star, it would appear to be in this area of its background. So the background stars would be whatever is in this blue square. If you shift now, say around your orbit of your planet, over to viewpoint B, and you look at that same star, it's going to appear to have moved based on its background. Because now it's going to look like this star is within whatever background is covered by this red square. So when you're at viewpoint A, you see the star within the blue square. When you're at viewpoint B, you see your star within the red square. The star didn't change, you moved. So because you're moving, you're seeing a different vantage point, it looks like the star has moved. So that is parallax, which we use in conjunction with some trigonometry to determine the distance to distant objects. So we use triangulation. So we have that viewpoint A position and that viewpoint B position. And if we know the distance between the two positions A and B, which we call our baseline, we're able to use some simple trigonometry to determine the distance, for example, to this tree. So we do this very often on Earth. This is very, very common to determine the distance to things, even just on the surface of the Earth. So you could actually use this, like this diagram. Measure your baseline between your two objects, measure the angles, the angle from where you're standing at B versus A to the tree. You can calculate the distance across the river to the tree. The larger you go, so the larger the distance that you're trying to measure, the larger the baseline will need to be in order to do this calculation. So if we were going to scale this up from instead of looking across a river to a tree, to across the solar system, out of our solar system to another star, we would need a very, very, very large baseline. So a huge difference between that position A and that position B. So what we do with astronomical triangulation, when we're trying to find the distance to a star, is we use our orbit as our baseline. So the orbit of the Earth is the largest change that we can, that's the largest baseline that we can have when we're on Earth. So we take a measurement in January, and then we wait and we take another one in July when we're on the other side of our orbit. So then our baseline is 2 astronomical units. So where the astronomical unit, remember, is the distance from the Earth to the Sun, so sort of the radius of our orbit, our baseline would be 2 of those because we're going from one side of the orbit all the way to the other side. So because the baseline is so large, this allows us to measure the distance to very far objects, and we're actually able to calculate super far distances, able to calculate the distance of these certain stars. So we're able to use these observations that are taken 6 months apart to measure the stellar parallax. So stellar parallax is the specific shift across that 2 astronomical unit baseline. It's usually measured in arc seconds. So when we're talking about stellar parallax, we know that we're talking about taking one observation and then another observation 6 months later. So we know that we're using our orbit as our baseline. So if you're discussing stellar parallax, if anything was determined via stellar parallax, we know that we used Earth's orbit as our baseline. Or I should say we used the diameter of Earth's orbit as our baseline. So with that, we have a new unit that is called the parsec. So the parsec is the distance to any star that has a parallax of 1 arcsecond. So these distances are huge. So we tried to find ways to make things easier to compare to each other, make numbers easier to think about. So we use this unit sort of as our base. So the distance to a star that has a parallax of 1 arcsecond is called a parsec. So a little unit reminder, the astronomical unit is the distance from the Earth to the Sun. It's the radius of our orbit. So when we use stellar parallax, our baseline is 2 astronomical units because it's not just the radius, it's the entire diameter. A light year is the distance that light travels in 1 year. And then remember that a degree is when we're talking about a distance on our celestial sphere. So a degree of that 360 degrees of the sphere. Within 1 degree, we have 60 arc minutes. Within 1 arc minute, we have 60 arc seconds. So it's very similar to hours, minutes, seconds, like on a clock. And now we have 1 parsec. So a parsec is the distance to a star that has a parallax of 1 arcsecond. So that's a small parallax. It's only 1 arcsecond, remember. So 1 parsec is a huge distance. It is about 206,000 astronomical units. So 206,000 times the distance from the Earth to the Sun would be the distance from the Earth to a star that is 1 parsec away. So we're actually able to calculate the distance to any object if we know how much that object has shifted within the sky. So if our baseline is that this is a typo. If the baseline is 2 astronomical units, sorry about that, over that 6-month period, we're actually able to calculate the distance to that object using our understanding of parsecs and stellar parallax. So we can calculate just using some rather simple math that we are not going to do in detail in this class, to determine the actual distance to that object, even if it's hundreds of thousands of astronomical units away from us. So when we measure parallax from Earth, if we look at a star, the star that's closest to the Sun, for example, has a parallax of 0.747. This is the closest star to the Sun, and we still see this parallax. The problem is, our atmosphere, if you remember, there's a lot of turbulence going on in our atmosphere, which causes blurring of objects that we're viewing. This is why telescopes are usually put away from cities, trying to put them up on top of tall mountains, because our atmosphere causes twinkling of the stars, causes blurring of the features. So stars will appear to be about 1 arcsecond in diameter. This can cause a huge uncertainty in the measurements of the parallax. If you're measuring a very small parallax, but the star itself is very blurry, you're not going to get a very good reading. You're not going to have much confidence in the actual parallax that you're measuring. So using this method, we can really only measure the distance to stars that are within about 50 parsecs of Earth. This is only about 10,000 stars, it's still a lot of stars, but compared to all the stars in the universe, we can only use this method to measure the distance of stars within 50 parsecs. Otherwise, it's too blurry to get a good reading. It's too blurry to rely on. It's too blurry to actually take valuable measurements. So this is not something that can be done super easily. As you remember, it's going to take 6 months to get 2 readings. And to do this for every single star, it has taken quite a bit of time. So the parallaxes of billions of stars have actually been measured from satellites since the 80s. So the cool thing about measuring the parallax from a satellite means that you're measuring from outside of our atmosphere. So on Earth, from, let's say, a telescope on Earth, we can only measure these 10,000 stars that are within this 50 parsecs. Otherwise, the data isn't good enough. It's not clear enough. Our atmosphere gets in the way. But if we're measuring from a satellite, which is outside of our atmosphere, but it's still circling around Earth, so we can still use the stellar parallax, we can still use that 2 astronomical unit baseline, we're removing the noise caused by the atmosphere, and we can measure the parallax of any star, billions of stars. So since about the 1980s, when we started using satellites to measure faraway stars, we've been able to build up a huge database of parallaxes and distance to faraway stars, even if they are farther away, I should say, than the 50 parsecs. So knowing the distance to each star is really important, especially when we're trying to learn about the star itself, learn more details about that star. When we think about brightness, we have what's called apparent brightness. So this is the brightness that we see from Earth. So how bright does the star look in the sky? Well, this is dependent on how far away it is from us. So a small, less bright star B that is closer to Earth could appear to be exactly as bright as this huge, very bright star A that's further away from us. So they look the same because star A is further away. Star B is closer, even though it's smaller, it's not outputting as much light, as much energy, it's closer to us. So they're going to look the same from Earth. But if we know the distance by using our stellar parallax, we'll be able to determine that star A is actually a lot more powerful. It's emitting a lot more energy, a lot more light. It's just further away. So by the time the light gets to us, they look the same. So this is taking this apparent magnitude chart that we've talked about, taking it one step further to actually understand more about these stars. Because we're not just looking at how bright are they to us, how bright do they look when we look up, but how much energy is this star actually emitting? We have to know the distance. So we have what is called intrinsic brightness. So intrinsic brightness is the amount of light that the star emits, the total amount of light that is emitted from the star. So in order to understand the intrinsic brightness, the real brightness of the star, we have to know the distance to the object. So we have to know the distance to that star, which we know we can calculate using our stellar parallax. So once we know the distance to the star, we can calculate the actual brightness, this intrinsic brightness. So the brightness is inversely proportional to the distance. Actually, it's inversely proportional to the square of the distance from the star. So as the distance increases, so as we're looking at stars that are further and further away, the brightness of the star is going to decrease. So if we double the distance to the star, so if we're looking at a star a certain distance and then looking at a star doubly that distance, the brightness will actually decrease by 4 times because it's the square. So the reason for this is as light radiates away from the star, away from the source of the light being the star, it spreads out and becomes less intense. Here we go. So let's say this is a star. I know in this diagram it's a light bulb. But as this light is radiated outwards in all directions, the same amount of light from distance 1 to distance 2, it's the same amount of light being emitted and spread over this area. So if we double the distance from 1 to 2, we'll see that the amount of light, or the amount of area covered by this light, actually increases by 4. So as you are further and further away from the light source, the brightness is going to decrease dramatically. So here's another diagram showing the brightness of the star is inversely proportional to the square of the distance, meaning as your distance increases, your brightness, as your distance increases, your brightness decreases, which makes sense if you think about it. So we also have what is called the absolute visual magnitude. So we have the apparent magnitude, which is how bright does it look. We have the intrinsic brightness, which is how much energy is it actually emitting. But it can be hard to compare with either of those units. So if we know the distance to the star, we can calculate the intrinsic brightness, and then we can calculate the absolute visual magnitude. So this, which you'll see big M, little v usually, this is the magnitude of the star if it were 10 parsecs away. So if we calculate the actual brightness of the star, and then we scale it to either be further away or closer, so that we pretend all stars are 10 parsecs away, then we see the intrinsic brightness at that distance. That is the absolute visual magnitude. When we assume everything, we scale everything to be 10 parsecs away so that we can compare. So let's say the sun, if we pretend the sun was 10 parsecs away, it would seem like a very, very, very average star. Its brightness would be only a 4.8. Visible to the naked eye, but not all that bright. Less bright than our brightest star in the sky, less bright than Venus. Remember that 6 is the cutoff for viewing with the naked eye. So we can scale all of our stars to be at this absolute visual magnitude cutoff of 10 parsecs, and then we can compare them to each other much more easily than saying, well, the intrinsic brightness is brighter here, but the apparent brightness is brighter for this one. It can be really difficult to compare when you're not looking at something scaled to the same factor. So we assume or pretend or calculate as if all stars were 10 parsecs away, so we can actually compare them to each other. Which one really is brighter? Which one is outputting the most energy? So that would be called the absolute visual magnitude. So what we can do, again, to look at the brightness or the energy radiated, is we calculate what's called the luminosity. So luminosity is the energy that's radiated in 1 second. So we report this in what's called solar units. So it's the L for luminosity, and then this symbol for the sun, which is a circle and a dot. And we can compare to the luminosity of our sun. So the L with the symbol for our sun is the luminosity of our sun. So we can look at different stars and compare them directly to our sun. So this star here, for example, has a luminosity of 170 solar units. That means it has 170 times more energy radiated than the energy radiated from our sun. So we can easily then calculate, which again we're not going to have to do in this class, these calculations, but we can calculate how much actual energy that would be using the energy value there for the solar units times the 170, and you get the actual energy that's outputted by this star. 170 times brighter than the Earth. Than our sun. So Cecilia Payne is a famous female astronomer that was the first to discover how much of each element is present using absorption information. So she determined that the sun is made of mostly hydrogen, and the rest of it is helium. And she was the first one to be able to give a number. Instead of saying the sun is made of hydrogen and helium, she was able to say it's about 90% hydrogen and the rest is helium. So she had an actual value for the percentages there. So she did other things too. She also discovered that the sun is very average. The chemical composition of the sun is just like all the other stars. And The spectra provides information only on temperature, but stars with similar spectra have similar temperatures. So the temperature of a star can range anywhere from about 2,000 to 50,000 plus Kelvin. Huge range in temperature depending on the star. So how do we actually estimate the temperature of a star? There's a huge range. How on earth do we know the temperature of a star? You got it. Black body curves. They're coming back. So what we're able to do is look at the peak wavelength that's emitted from the object. Remember, this is Wien's law. We can determine the temperature of the object by looking at the peak wavelength of emittance. So we can be even more specific by using Cecilia Payne's idea of what's called the Balmer thermometer. So we use the spectra of a star to determine the temperature of the star. So this depends on what we call Balmer lines. So the Balmer lines are the spectral lines of hydrogen, but only within the visible. So remember that hydrogen's going to emit and absorb in other wavelengths as well. But within the visible, these are the only 4 spectral lines that we see from hydrogen. So there's a red, there's a light blue, and there's 2 purples, 2 violets. So the Balmer lines can be very, very helpful to help us determine the temperature of any star. So let's see. We're able to use, because we know, Cecilia Payne says, most stars are made of mostly hydrogen. So every star that we're looking at is going to have hydrogen. So we're able to use these spectral lines for every star. So we call it the Balmer thermometer, and we're able to use the strength of these Balmer lines to determine the temperature. So the strength of the Balmer lines, meaning how clear are the Balmer lines, it's going to depend on the temperature of the surface of the star. So the absorption lines of these Balmer lines of the hydrogen is only going to be produced by atoms with electrons in the 2nd energy level. So not at the ground state, not at the 4th energy level, at the 2nd energy level. So when atoms are excited to that 2nd energy level, that's where we're going to see the absorption lines of the hydrogen, which would be where we would see this Balmer pattern, this Balmer thermometer. So a cooler star, a very cold star, I shouldn't say very cold, I should say cooler, because all stars are hot, but a relatively cool star, there aren't going to be enough collisions to excite the electrons into that 2nd energy level. So they're not going to be absorbing photons in the Balmer series. So with the cool star, we're not going to see the Balmer absorption lines. Now, a very, very, very hot star, there are way too many collisions. All of the atoms will be too excited. There aren't going to be enough left in that 2nd energy level. They will all have jumped to further energy levels. The star's too hot. Meaning, with a hotter star, we still will not see the Balmer series pattern. Now, an intermediate star, a medium temperature star, is sort of the Goldilocks zone. So this is where a large number of our electrons will be excited. They will get excited into that 2nd energy level, but not too much higher, meaning they will absorb photons at that Balmer series. So we will see the pattern of the Balmer lines being the 1 red, the 1 light blue, and the 2 purple with an intermediate temperature star. So not a star that's too cold, not a star that's too hot, but those medium temperature stars. So hot and cold stars, we're going to see weak Balmer lines, or they will not be very visible. Intermediate stars, we're going to see very strong, very clear Balmer lines. So we can use the strength of the Balmer lines to determine the temperature. So if we had a medium strength Balmer line, so here is the line strength versus temperature. So let's say here we have weak at the bottom, strong. Here's our line strength. And we're looking at the hydrogen curve. So where our line strength matches up, we can say, okay, so our star could be about 8,000 Kelvin, or it could be about 20,000 Kelvin. Great. that narrows it down. We know a little bit more, but how do we know which one? So with just this information, knowing we have a medium strength Balmer line, it could be two of these, it could be either of these two temperatures. So how do we figure out which one is right? Is we plot the lines for other elements, not just hydrogen. So we can then move on from just hydrogen to other elements. So the temperature is going to have a really similar effect on all of the spectral lines of all elements, not just hydrogen. So hydrogen is the starting point. Hydrogen is what we call the Balmer thermometer. But then from there, we can get even more precise by doing the same process, plotting these same lines for other elements. So for example, here we have calcium added to this graph. So if we have a star that has medium strength Balmer lines, and we find that it has very strong helium lines, what is the temperature of the star? So here we would look for the overlap. So for hydrogen, which is this orange, it has about medium strength. So medium strength matching up with strong helium lines, which is these green, we're going to look for that overlap. So that means our star is about here. The star can't be on this end of the hydrogen graph because we know it also has strong helium lines. So the star must be about 18,000, 20,000 Kelvin. So if we still have a medium strength Balmer line, meaning medium strength hydrogen, and about medium strength iron lines, what would our temperature be? It would be something much cooler. So we would see something around, 7,000 Kelvin. So we look for the overlap. So we use more than just the Balmer lines to get even more precise and determine the exact temperature of any star. So when we think about our Balmer lines, astronomers in the end of the 1800s developed what were called spectral classes. So there's 7 classes or types, spectral classes, that are according to temperature. So it goes spectral class O, B, A, F, G, K, M, from hottest to coolest. So we like to use the phrase, oh boy, an F grade kills me, to remember O, B, A, F, G, K, M, from hottest to coolest. So it's in temperature order. O, spectral class being the hottest, which you'll notice has weak hydrogen lines. M, spectral class being the coolest, which also has weak hydrogen Balmer lines. But we see that in the middle, so these more medium temperatures, we see the stronger hydrogen Balmer lines. So remember, we see those strong Balmer lines in the medium intermediate temperature stars. So each of these spectral classes also has 10 subclasses underneath. So with A, you have A, 0, 1, 2, 3, 4, etc. But these are the main spectral classes when we are separating stars into groups or classes based on temperature. So the strength of our spectral lines depends, remember, on temperature. So if we are going to look at our hydrogen Balmer lines, remember we have the 1 red, the light blue, and the 2 purple. So if we look at our spectral lines of different stars in these different spectral groups, so B, A, F, G, K, M here, and they're also plotted in temperature order. So the temperature of the B star and the O star, of course, is hotter than the temperature of the K and the M star. But I stretched out this, it's not the same scale, but I stretched out this diagram of the hydrogen emission spectrum to try to match it up with this diagram. We'll notice that we do see those dark lines because the hydrogen's being absorbed there. So you'll see in these medium temperature stars, these intermediate temperature stars of the A and the F, we see those strong Balmer lines very, very clearly. Here's the 2 purple, here's the blue, light blue, and here's the red. So if we're looking at any star, within these spectral classes, we'll see that the spectral classes in the middle with the medium intermediate temperatures are where we very clearly see these strong Balmer lines. Whereas the cooler stars, the hotter stars, we do not see. We can see them, they're a little bit weaker, but it is not as clear as the medium temperature stars where we know we have those really strong Balmer lines. So we can also do this looking at spectral graphs. So we know that where we see a dip in our spectral graph is where we have an absorption line. So if we look at these spectral graphs, these spectral lines of different stars, here we have an O star all the way through an M star, plotted here in intensity and wavelength on the X. We can actually still see our hydrogen Balmer lines. So how would we determine the temperature of these stars? Well, they're labeled, so we know that the O is going to be the hottest, the M will be the coolest. But we can also look at the peak of the curve. So the peak of the curve is at the shortest wavelength for the hottest star. The peak of the curve is towards the middle for the medium stars. The peak of the curve is towards the longer wavelength, less energy for the cooler stars. But you'll notice that in our intermediate stars, the A and the F, we can really clearly still see the hydrogen Balmer lines. So here is the dip in the red. We have the dip in the light blue, and then the dip in the purple. Oh, excuse me. This would be the dip in the light blue. Here it's labeled green, but this is the light blue wavelength, and then we have the double dip in the purple or the violet. So you can see those hydrogen Balmer lines even here in the spectral graph, and you can see them very clearly in our intermediate temperature stars, but not at all in the cooler stars, and not very much in the warmer stars either.